Welcome, cosmic explorers, to another mind-blowing journey through the depths of space. Today, we're diving into a discovery that has scientists and stargazers alike buzzing with excitement and a hint of trepidation. The James Webb Telescope, humanity's most powerful eye in the sky, has made a groundbreaking observation that could change our understanding of the universe. Strap in as we explore the eerie revelation of city lights on Proxima B, Earth's closest exoplanet neighbor in the habitable zone. Could this be the first evidence of alien civilization? Let's find out. For centuries, humanity has pondered the existence of life on other planets. Now, with the advent of the James Webb Space Telescope, the most advanced telescope ever built, we are closer than ever to answering that profound question. Observations of Proxima Centauri, the nearest star system to Earth, located just 4 light-years away, have revealed intriguing anomalies on one of its planets, Proxima B. These anomalies, identified as artificial lights, have sparked intense debate and curiosity among the scientific community. Could these lights indicate the presence of intelligent life? Join us as we delve into the James Webb Space Telescope's groundbreaking discovery of city lights on Proxima B, a finding that could potentially rewrite everything we know about life in the universe. Until now, Earth has been the only known home to life. Since the dawn of civilization, humans have wondered if we are alone in the vast expanse of space. To pursue this interstellar inquiry, American astronomers Jill Tarter and Thomas Pearson initiated the Search for Extraterrestrial Intelligence (SETI) project in 1984. This nonprofit organization aims to capture spaceborne radio signals. Given that radio waves can travel vast distances, they are more likely to be detected. The effort is supported by the unique Allen Telescope Array, consisting of 42 radio telescopes, designed to listen for signals from beyond our world. In the California Cascade Mountains, despite 30 years of searching, no definitive alien signals have been detected. However, the launch of the James Webb Space Telescope has significantly advanced our quest to explore distant, uncharted planets orbiting stars far beyond our own. As the largest telescope ever deployed, stationed about 1 million miles from Earth, it boasts incredibly sensitive detectors capable of observing the cosmos like never before. 2 decades ago, we knew of no planets outside our solar system. Since then, over 4,000 exoplanets orbiting other stars have been identified, according to NASA. With the universe potentially housing trillions of exoplanets, the search for life beyond our solar system has expanded. One promising area of research involves the search for extraterrestrial plant life. The Galileo spacecraft, on its way to Jupiter, directed its instruments back towards Earth, discovering clear evidence of plant life through the detection of the vegetation red edge, VRE biosignature. This signature, a combination of red and infrared light reflected by plants, suggests that a planet rich in vegetation, similar to Earth's jungles, would emit a strong and easily detectable VRR signal. The James Webb Space Telescope, JWST, is set to measure the VRE of distant, Earth-like planets situated in the habitable zones around their stars. These measurements could serve as crucial indicators of life in the atmospheres of exoplanets. When sunlight passes through a planet's atmosphere, the JWST's observations may reveal the presence of biosignatures, pointing towards the potential for life on other worlds. As it traverses the atmosphere of a planet, the James Webb Space Telescope, JWST, is equipped to detect the unique signatures of light by employing spectroscopy. This technique identifies the specific wavelengths absorbed by atoms and molecules in the atmosphere, creating a distinctive fingerprint that JWST can recognize. This process enables scientists to analyze the atmospheric composition and assess the potential for life. Planets the size of Earth, with atmospheres rich in oxygen, nitrogen, and carbon dioxide, are prime candidates for harboring life. The search for extraterrestrial intelligence extends to detecting signs of technological life through elements uncommon in a natural setting. For example, chlorofluorocarbons, CFCs, Synthetic compounds used in refrigeration and cleaning products would be easily identifiable signs of technological civilization to observers from afar. If JWST were to find CFCs in the atmospheres of exoplanets, it would serve as a definitive marker of civilization. However, life on exoplanets might bear little resemblance to life as we know it on Earth. Even on our planet, extremophiles, organisms that thrive in conditions lethal to most other forms of life, can seem utterly alien. This category includes primarily bacteria that can survive extreme environments, showcasing the vast diversity of life possible under different conditions. For instance, some organisms can endure temperatures up to 250 F, highlighting the resilience and adaptability of life. Such discoveries underline the potential for finding life in seemingly inhospitable environments across the universe. Given that planets similar to Earth are more conducive to supporting life compared to those with extreme temperatures or acidic environments, it makes sense to prioritize them. Ideal candidates would be planets that maintain temperatures suitable for liquid water to exist on their surfaces and orbit around a stable star. Our Sun, classified as a yellow G-type star, is an example of such a star. While these stars are rarer and generally have shorter lifespans, they are traditionally considered prime targets for the search for life. However, the vast majority of our universe's exploration might shift towards planets orbiting red dwarf stars. These stars are more common, have lower luminosity and temperature compared to our Sun, and offer a longer window for life to potentially develop and evolve into complex organisms due to their extended lifespans. Approximately 40 light-years from Earth, the TRAPPIST-1 planetary system is set to be one of the James Webb Space Telescope's JWST initial targets. This system orbits a tranquil red dwarf star and comprises 7 Earth-sized rocky planets. Notably, 3 of these planets fall within the so-called habitable zone, where conditions may allow for liquid water on their surfaces. Despite the TRAPPIST-1 star's significantly smaller and cooler mass than our Sun, it emits sufficient light that could support the conditions necessary for life as we understand it. Proxima Centauri, a red dwarf star located 4.25 light-years from our Sun, offers the most promising opportunity for humans to possibly observe city lights beyond our solar system. Due to its significantly lower brightness, about 600 times fainter than the Sun, a planet would need to orbit 20 times closer to Proxima Centauri than Earth does to the Sun to potentially harbor life-sustaining liquid water. On August 16, astronomers made a merely 4.6 million miles from Proxima Centauri, subjects it to intense solar winds, which could strip away any atmosphere. Nonetheless, its proximity to its host star also means it receives sufficient sunlight for Earth-like temperatures and liquid water, provided it retains an atmosphere. The close orbit suggests Proxima B may be tidally locked, always showing the same face to its star, similar to how the Moon orbits Earth. Proxima Centauri's mass is just 1/8 that of the Sun, and it shines much less brightly than expected for a star so close to a potentially habitable planet. Despite being only 5% as far from its star as Earth is from the Sun, conditions on Proxima B could allow for the existence of liquid water if the planet has an atmosphere to protect it. Despite receiving only 65% of the energy from its star compared to what Earth gets from the Sun, the planet in question is not particularly hospitable to life. It is believed to be tidally locked, meaning it always faces its star with the same side, resulting in permanent day and night regions and causing drastic temperature variations. Additionally, it is exposed to 100 times more high-energy radiation, including X-rays and ultraviolet light, due to its closeness to Proxima Centauri. This radiation increases during stellar flare-ups, bombarding Proxima B with high-energy particles. The existence of a protective magnetic field similar to Earth's could shield the planet from some of these harsh conditions. However, the atmosphere of tidally locked planets is theorized to be vulnerable to rapid degradation. This is due to the potential for volatile gases to freeze on the night side, leading to atmospheric collapse. Earth's atmosphere benefits from continuous replenishment through volcanic activity, and a strong magnetic field helps retain this atmosphere. Without concrete knowledge of Proxima B's volcanic activity or the strength of its magnetic field, it's challenging to determine the presence of an atmosphere. An atmosphere, however, would imply the possibility of oceans and, by extension, the conditions necessary for life as we understand it. The combined factors strongly suggest the potential for life, sparking intense curiosity about whether Proxima B harbors an advanced civilization. Such a civilization might utilize solar panels to cover the day side, generating electricity to illuminate and heat the night side, which would otherwise remain inhospitably cold and dark. The discovery of Proxima B has ignited a scientific race to observe if it transits across the face of its star from Earth's perspective. These transits would allow scientists to ascertain the planet's size and mass, leading to an understanding of its density. This information is crucial for confirming Proxima B's rocky nature and deducing the composition of those rocks. During a transit, the way starlight interacts with the planet's atmosphere could reveal significant details about its characteristics. However, the chance of the planet's orbit aligning in such a way that allows for a transit observable from Earth is slim, at only about 1.5%. The star's tendency to emit flares adds another layer of complexity to these observations. According to astronomer David Kipping from Columbia University, the star's activity makes analysis challenging. As stars heat up, a rocky planet like Proxima B absorbs sunlight and re-emits it as infrared light. Yet, the infrared radiation emitted by rocky planets is distinct from that of stars like Proxima Centauri. The James Webb Space Telescope, specifically designed to study infrared light, could play a pivotal role in uncovering Proxima B's secrets. Detecting its infrared heat signature could be the key to understanding the planet's surface and atmospheric conditions, potentially bringing us closer to discovering whether life as we know it could exist there. The James Webb Space Telescope, JWST, the successor to the Hubble, is particularly adept at analyzing the infrared spectrum, which is crucial for detecting a planet's atmosphere. Its capabilities extend to potentially observing artificial lights on the night side of Proxima B, even if these lights are as dim as those produced by our civilization on Earth. JWST's ability to detect such illumination hinges on it being within a frequency band 1,000 times narrower than the broad spectrum of daylight Proxima B receives. Proxima B's day side is speculated to be densely packed with solar panels, reflecting its star's light due to its unique spectral edge. As the planet orbits its star, day and night experience similar patterns, with cooler temperatures at night following warmer daytime highs. The temperature variance between day and night is contingent on the planet's composition, whether it consists solely of bare rock or has an atmosphere and oceans that can distribute heat. In the absence of an atmosphere, the temperature difference between Proxima B's day and night sides would be stark. The day side, absorbing all the energy from Proxima Centauri, would emit it as black body radiation, allowing for precise calculations of the expected radiation. Conversely, without heat distribution, the night side could resemble a frigid wasteland. A less significant temperature differential would suggest the presence of an atmosphere, moderating the climate across the planet. The James Webb Space Telescope, JWST, is set to significantly advance our understanding of exoplanetary atmospheres. It will take JWST only 11.2 Earth days to measure the infrared, IR radiation emanating from both sides of Proxima B, following a complete orbit around its star. If Proxima B possesses an atmosphere, the next step will involve analyzing its composition. Detecting gases such as oxygen, water vapor, and methane could point towards potentially habitable conditions or even the presence of life. Capturing starlight as it reflects off or passes through the planet's atmosphere is a challenging endeavor. While JWST is a formidable tool for studying the closest potentially habitable exoplanets, it wasn't specifically designed for the detection of extraterrestrial life. its capabilities are somewhat limited to observing changes in atmospheric concentrations of methane, carbon dioxide, and water vapor. Unfortunately, JWST cannot detect unbonded oxygen, a key indicator of life, although certain combinations of detectable gases may hint at biological activity. Future ground-based observatories, like the Extremely Large Telescope, ELT, expected to commence operations in the mid-2020s, will be equipped for more in-depth atmospheric analysis. These observatories may be able to detect substances such as ozone, which JWST is also capable of observing. Together, these instruments will significantly enhance our ability to infer the presence of atmospheres on distant worlds and assess their potential habitability. As the James Webb Space Telescope, JWST begins its operations, it is expected to deliver insights that will be pivotal for at least the next decade. Future space telescopes, even more advanced, may utilize innovative techniques to obscure the overwhelming brightness of a planet's host star, thereby enhancing the visibility of light reflected from the planet. This concept is akin to using your hand to block direct light, improving your view of more distant objects. Future telescopes could achieve this through the use of small internal masks or large external structures resembling umbrellas. Once the starlight is effectively blocked, analyzing the light reflected off a planet becomes significantly easier. However, a major challenge in this endeavor is that many gases indicative of terrestrial life can also be generated through non-biological means. For example, methane can be emitted by both biological entities like cows and geological processes such as volcanic eruptions. Similarly, sunlight can split water molecules into oxygen and hydrogen, a process also mimicked by photosynthesis in plants. In the quest to discover alien life, astronomers are likely to encounter numerous false positives. A detailed understanding of a planet's geological and atmospheric characteristics is crucial to determine whether observed phenomena might mimic biological signatures, thereby helping to eliminate these false positives. The next generation of exoplanet research is poised to potentially provide the compelling evidence needed to advance our understanding of life beyond Earth. The initial findings from the James Webb Space Telescope offer a glimpse into the profound discoveries that lie ahead in our quest to determine the existence of life beyond Earth. This question stands as one of the most pivotal inquiries within the scientific community. Life may be widespread across the universe, or conversely, Earth could be a unique oasis of life in the vast expanse of space. Regardless of the outcome, understanding our place in the cosmos is bound to necessitate significant philosophical or psychological shifts in our collective perspective. The realization of our situation, whether we are alone or among a universe teeming with life, will profoundly impact our view of existence. In an unparalleled feat of astronomical detection, the James Webb Telescope has captured what appears to be artificial lights on the surface of Proxima B. This exoplanet, orbiting the red dwarf star Proxima Centauri, has always been a prime candidate in the search for extraterrestrial life due to its Earth-like qualities and potential for liquid water. These observations could signify the presence of an advanced civilization capable of lighting up their world in a way eerily reminiscent of our own cities at night. The possibility of discovering alien life has always been a tantalizing prospect for humanity. The detection of city lights on Proxima B not only boosts the chances of life beyond Earth, but also suggests the presence of intelligent beings with technological capabilities. This discovery prompts us to reconsider our place in the cosmos, the potential for interstellar communication, and the profound question of whether we are truly alone in the universe. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and as sessions with experts. Your membership will grant you the chance to participate in live Q and a sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.